Welcome to our third lesson on 2 and 3-dimensional wave fronts. As said, today we'll be looking at single-slit diffraction. Now up till now we've looked at diffraction usually either in sound or in a water wave. And we said that if you've got wave fronts, remember those are the crests as seen from top, passing through in this case a small aperture, which means an opening, then we would have seen diffraction as it is viewed by water waves. But now what we're going to do is we're going to shine light of a specific frequency, and we're going to call it monochromatic light, and then we're also going to observe as we shine it through a single slit, that means the small aperture, that there will be a pattern that we can see on the other side on a screen. Now this diffraction of light is going to contribute to light's wave nature. Light has basically two types of natures. One is what we call the wave nature and the other one the particle nature. Now in grade 10 you have briefly touched on the particle nature when we looked at electromagnetic waves. And that is basically meant that light as you see it is not like the sun with straight continuous rays of light. It is actually small packets of energy that move just so fast that it looks like one continuous line. And that was basically explaining to us the particle nature of light. But when we're going to look at the wave nature of light, that's going to be explained by diffraction. And that's when we're going to see here in our single-slitted diffraction pattern. Now, as I said, we're going to be using monochromatic light. And that basically means that it's light of a single frequency. That mono means one, so this is light with only one frequency. Now when you looked at the electromagnetic spectrum of visible light in grade 10, we said that light is actually broken up into 7 colors, which starts with red, which in this case has the longest wavelength. So let's just, for our explanation, remember to write in here, it's got the longest wavelength, but if it's got the longest wavelength, then it means it's got the shortest frequency. Because our light, if the speed stays the same, like it does for all electromagnetic waves, which is 3 times 10 to the power of 8 meters per second, then it means as my wavelength decreases with time, my frequency will increase. And that's exactly what we see. My red lights start off with, of the visible light spectrum, the longest wavelength but the lowest frequency, and then it increases as we're going to go from red, orange, yellow, green, blue, indigo, and violet to waves that has got a shorter wavelength but a higher frequency. So if I'm talking about monochromatic light, I'm talking about light of a single frequency. That means it's either red, or it's orange, or it's yellow, or it's any one of these one colors only. So what we're going to do is we're going to have a laser. A laser means it's going to shine one light of color only. And it's going to shine that color of light. Now note that light is a wave. So light also have crests and troughs. But if we view it from the top, then we'll see only the crests as wave fronts. So these are the lines that you see here in blue. Now note here is my single slit. That means there's an opening in between these two obstacles, and then as we know there would be diffraction occurring. According to our Huygens principle, there is that bending of light as it passes through this aperture, and then what we're going to do is we're going to put a white screen on the other side, and we're going to let this diffraction being shown onto the screen. Now once we do that, we see the following pattern as you observe it here. On the right hand side, you'll see that right in the middle there is a broad, and we're going to call it bright band, but the bright band basically refers to the specific color that you've used. So if you've used blue, this will be a bright blue band. If you've used a red light, then it will be a red band. So first off, you've got a broader, that means a wider and a bigger bright band in the middle. And followed on either side, you're going to have a dark band, followed by another smaller bright band than the one in the middle, followed by a dark band and bright band, and so they continue onwards. Now you would note that on the side here of the right hand part, I've indicated to you the type of interference that we see. Now this diffraction actually then has constructive interference in the middle where this bright broad band is, and you then see it as a greater amplitude. where we have our dark bands, we've got going to have destructive, and the rest of the bright bands is also constructive, but it's not as great as your central bright broad band. So all your bright bands, which we refer to as the color of the light, is going to be constructive interference, and all the dark bands is going to be seen as destructive interference. So your single slit diffraction pattern is basically characterized by a central bright, which in this case could be blue, band, followed by alternating dark and bright colored bands on either side of the central bright band. Now the degree of diffraction, that means the amount of bending, basically depends on two things. First off is your slit width. And slit width is indicated as my small letter w over here. So diffraction is inversely proportional to slit width. That means the smaller the slit, the greater the diffraction. And if you then have a smaller slit through which this wave is going to pass through, and as said we've got a greater diffraction, then it means the pattern observed on the screen will have a greater central broad band, followed then by narrower alternating dark and bright bands. If we though go look at the second characteristic, this is when we have our wavelength. Now diffraction is directly proportional to the wavelength, and here we're going to go back again to your visible spectrum of colors to explain. Now remember we said diffraction is directly proportional to the wavelength. That means the greater the wavelength of your specific color of light which you're shining, the greater the diffraction would be. So that means to us, if we take for example red light and we compare it to blue light, when I have red light as my monochromatic light that I shine through a single slit, remember red light has got a greater or a longer wavelength than our blue light has. That means my red light with the longer wavelength, which means a greater diffraction, will then have a broader central band with its alternating dark and bright bands on either side. But if I go and look at my blue light that has got a shorter wavelength, that means less diffraction, then its central band would be smaller compared to that of red with its alternating dark and bright bands following on either side. So you need to make sure that you read the question as to whether they tell you compared to red or blue, and then you need to have a specific indication of which one of the two has got the greater wavelength. So basically that width of that central bright band will then change if I've got a greater wavelength, which basically means the color of light. That central bright band will also change depending on the slit width size, and also the distance away that the slit and the screen is from each other. Now we already know that if I've got a greater wavelength, I'll have a greater central broad band. We also know that the size of the slit, the smaller the size of the slit, then the greater we'll have our central bright broad band. And when we talk about the distance between the screen and the slit, the closer the screen and the slit is to each other, the smaller the central band will be. But the greater the distance is between the screen and the slit, then the broader the band we will observe. Now the question which I would like you to go and attempt is to explain the difference observed between using monochromatic green light or monochromatic blue light in your single slit diffraction experiment. Now when we're going to look at green light and blue light, we need to take into consideration their specific wavelength. Now if we go back again to our electromagnetic spectrum, remember that green light was still before blue light. Therefore it had, in this case, a longer wavelength than blue light does. And that would mean to us that green light is going to experience more diffraction, because the relationship between diffraction and wavelength is directly proportional. And if green light experiences more diffraction, we mean that we will see a greater central bright broad band for green light specifically, and our blue light will then obviously have a smaller central bright band. Now in our next lesson we'll be looking at some questions that you can expect in tests and exams.